Yeah, so if we're ready, I can start.
Okay. Thank you everyone for coming out for this special talk by Yami, former president of Math Club. Tonight he will be talking to us about complete regular dessins, and we hope you enjoy the talk. Thank you very much.
Okay. All right. So I'll start. I would someone like make sure the camera is following me when I switch the board. All right. So my name is Ajay, and yeah, I'm going to talk about complete regular dessins, which is like a project that I've been working on. All right. So let's just start. Great. So the goal of my talk is going to be to explain these two pictures, and eventually we're going to say that they're the same picture. So maybe like just an open question to you guys, like what do you see similar between these two pictures? Do they look anything like each other, or can you maybe spot something? Or like what do you think is similar between them? Yeah.
I was just going to say they're color coded in the same shades.
Mm-hmm. Right, so they're color coded. Okay, I didn't notice they were the same shape, but okay. Okay. Anything else?
It's the right one is like unfolded
Mm-hmm.
to 2D.
Mm-hmm. Yeah. Oh, by the way, so this up here, when you said unfolded, that's a good point, because you might not see it, but there's these arrows on the top over here, and arrows on the bottom here, and arrows on the right and left, and they're arrows to identify the sides. So what you want to do is actually take this top side and identify it with this bottom side. So if you drew a picture of this, well, whatever, so it's a square, right? But then you identify the top and bottom, and you identify the left and the right. So what shape do you get when you do this?
Square.
Torus? Yeah. This is a torus, right? So like maybe I'll identify the top and bottom first, so it looks like this. And then I have the left side identified to the right side. Okay. And then you need to identify those two sides together, and you get a torus, right? So really, what this thing on the right side is, it's this kind of funny thing. Okay, so there's this color coding on here, and that's really a color coding on the torus, right? So I have this nice kind of diagram here. Okay, I'll try not to draw it perfectly, but let's see. So this kind of thing, and then this becomes a sort of I didn't draw it very well, but the point is that this image on the right is actually a type of color coding on the torus, and so if that's what this is, and this somehow okay, so we don't know what the connection is right now, but yeah, did you want to say something?
Yeah, what are the black things?
Right. So these black things over here, they actually are going to correspond to these black edges here. So that's one similarity you could have pointed out, right? So like here you have these black edges here, and then here you have these black edges here. Also, this is a two-dimensional surface. This is also sort of looks like a surface. So we're going to see, like, we'll see actually. But that's basically the point of this talk. Okay, so here this is a torus. This is somehow supposed to be a torus as well. And here we have this kind of thing. Okay, so let's say what this right side is further. So I'm calling this a 5-color map on the torus. So here's an open-ended question. Give the definition of a map. What is a map? So this is an example of one. What is a map?
assigning colors to regions.
Basically, right? Any other suggestions? Okay, so I'll give you a formal definition now. So a map is an embedding of a graph into a surface such that the complement of the image is a disjoint of topological distance. So, okay, maybe this doesn't make any sense, but this is a map because what is it? So this is a surface, like I said, it's a torus, right? And then we have an embedding of a graph inside of this surface. So the specific graph that we have is a complete graph on 5 vertices. So K5, this is the complete graph. On 5 vertices. So what is a complete graph? It's just a graph where so on 5 vertices, usually you have 5 vertices. And then complete means every pair of vertices has an edge connecting them. So if you drew it in the plane, it would self-intersect, and it looks like a pentagram, right? So that's the complete graph on 5 vertices. But what I'm doing is I'm embedding this into this surface. So on the plane, it self-intersects, but on this torus, it doesn't self-intersect anymore. And yes?
The regions are vertices?
So there are 2 ways you could see this, but in here it doesn't matter. So here I'll just say these are the vertices. So I have 5 vertices here. 1, 2, 3. So if I label these 1, 2, 3, 4, 5, then I also have 5 vertices here. 1, 2, 3, 4, 5. And the point is that every pair of vertices on this torus is adjacent to each other. So you can look here. This 1 is connected to 5, and 2, and 3, and 4. So 1 is connected to every other vertex. And the same situation is happening at every other vertex. So this 2 is connected to this 1. It's also connected via this edge to 5. And via this edge, so I didn't draw this well, but if I go up here, then I'm supposed to go straight down here to here. So if I go up here, I'm supposed to go down here, and then so this way you're connecting to 4, and then and then this way you're going down and connecting to 3. So this 2 is also adjacent to every other vertex.
How, for example, the 3 and 5 are connected?
3 and 5, so it's the same situation. It looks exactly the same at every vertex. But yeah, 3 and 5 are connected. You go this way. You go, I guess, this way.
Just a question.
Yes?
What if you, instead of drawing straight lines, do curved lines? Would you also do the same plane instead of a torus?
Yes, that's a very good question. Can you embed K5 into the plane? Any ideas? What do you guys think?
No.
No. Okay. Well, is there a reason?
It would be painful if you try it.
Yeah, so let's try it. So I can put 1, 2, 3, 4, 5, and then maybe 1 is connected to these, but then 2, is connected to 3 and 1, but to go to 5 I need to go this way, and then to go to 4 I need to go this way, and then 3, now I can't connect 3 to 5 anymore, right? So I can't go this way because there's an edge. I can't go out, right? So yeah. So this is not a proof, but it's actually true that you cannot put K5 does not embed into the torus. So I am denoting my graph by K5, that means a complete graph on 5 vertices. And the torus, this is genus 1 surface. So the genus of the surface is the number of donut holes it has. So like the torus has genus 1, the sphere has genus 0, and the double torus has genus 2. Right. So you can't embed K5 in the torus, but okay, you can embed K5
In the plane.
oh, my bad. This is 0. You can't embed K5 in the plane or in the sphere, because the sphere is just almost a plane. If you remove a point from the sphere, it's like a plane, right? But you can embed K5 in the torus. Okay, thanks for checking that. Any questions? Yes?
What are those sigmas?
Right, so sigma is standing for the surface of genus G. So sigma G is surface of genus G. So sigma 0 is the surface of genus 0, so it's just a sphere. Sigma 1 is the surface of genus 1, so it's just a torus that has 1 hole. This has 0 holes, and this has 2 holes, like a 2-hole donut. Okay, right. So that's what a map is. A map is an embedding of a graph into a surface such that the complement of the image is a disjoint union of topological disks. Now what that means is here this is an embedding of K5 into the torus, and the complement of the image is just a disjoint union of disks. I mean, what is one connected component of the complement? It's just maybe this part, the shaded region. So like each of these shaded regions is topologically just a disk. Okay. Yes. And the definition, a complete graph on n vertices is a graph with n vertices and a single edge between each pair of distinct vertices. So this is the complete, this is a 5-color map, and it's an embedding of a complete graph on 5 vertices into the torus. Okay? So here's another example, the 7-color map, or Hewood map. 7-color torus. So this is, I have a model of this. So Professor Weierstrass crochets models of these maps. So this is a 7-color torus. This is a small one, but she has a bigger one. It's a map on the torus that consists of 7 faces. Right. And the point is that so here is a schematic visualization of the 7-color map on the torus, and yeah. So this is the front side of the donut. This is the back side of the donut, and this is the graph embedded inside of it. The complement is a bunch of these faces. These faces are colored over here, and yeah. Okay. So okay, maybe I should have said something more. You can also have a planar representation of this map. Okay, I'll just skip that. Right. So this is a dual of the Hewood map. So here you have this 7-color map in the torus, and the dual of a map is just going to replace all of the faces in the map with vertices, and all of the vertices in the map with faces. So if this had 7 faces, the dual map is going to have 7 vertices. So every face is replaced with a vertex, and every yeah. So this has 7 vertices, and the point is that the Hewood map is also has the property that every face is adjacent to every other face. So you can see that from this picture over here. You can look at 1. It's adjacent to 7, 5, 6, 2, and then going around the back of the torus, 1 is also adjacent to 3 and 4. So 1 is adjacent to 7, 5, 6, 2, and 4 and 3. So those are all of the numbers. 7, 5, 6, 2, 4, 3. Yeah. Okay, and by symmetry, this map also has many symmetries. And it's easier to see that every face is adjacent to every other face just by exploiting the symmetry. So if I look at 1, that face is no different from 7. And the same argument that I did to show that 1 is adjacent to every face also applies to 7. Just by doing a rotation of the map, you can see that the same thing is true for the face. Like 7 is also adjacent to every other face. And so is every other face. Every face is adjacent to every other face. So what that means is that when I look at the dual map, this is going to be an embedding of the complete graph on 7 vertices into the torus. So, yeah. Okay, so this is another example of an embedding of a complete graph into a torus. Okay, so these are examples of complete regular maps. So a complete map is an embedding of a complete graph into an oriented surface. And here are a bunch of examples. So here is the first one we started with. This is the embedding of K5 into the torus. And then this is the dual of the Hewitt map. This is an embedding of K7 into the torus. And this is a tetrahedron. This is also a complete regular map. So this is, how many vertices does this map have? 4, yes. And what is the genus of the surface that it's sitting on? 0, yeah. So this is the tetrahedron, the regular tetrahedron, is an example of a complete map. It's K4 embedding into the sphere. So these are all examples of complete maps, but they're also regular maps. So explaining regularity is a little bit more complicated, but the idea is that regular maps have a large amount of symmetry. So this tetrahedron here has all of these rotational symmetries. I can rotate it around and swap one face with the other. And yeah, so there's this whole large number of symmetries. And one way to define regular, and the only way that I need for this talk, is to say that if the number of symmetries is n times n minus 1, where n is the number of vertices in the complete graph, then it's regular. So this is just a way to say that there's a large number of symmetries of the map. So this tetrahedron, it has 4 times 3 symmetries, which is 12. So there are 12 symmetries of the tetrahedron. And you can check just by seeing how many different kinds of rotations can you do that leave the tetrahedron unchanged. So you can send one face to any other face, and then you could send that face in 3 different ways. So there are 4 faces and 3 edges to each face, so there are 12 symmetries or automorphisms of this map. Okay, so if that didn't make sense, it's not too important. Just regular just means it's symmetrical. There's lots of symmetries in this map. So I'm studying complete regular maps, and the specific example I'm interested in for this talk is K5, the complete graph in 5 vertices, embedded inside of the torus. Okay. So that's all of that. Are there any questions about what complete regular maps are, what it means, or anything like that? Okay.
Wait,
Yes.
do symmetries always have to be rotational? Or is it like complicated?
Yeah, so no, they don't always have to be rotational. So this torus here, this has rotational symmetry. I can do a rotation like this. But that's not going to give you all of the symmetries of the torus. So these rotations, maybe that just gives you like 7 rotations, but there are going to be more symmetries, and those are going to be from like putting this torus inside out, or like that. And it's much easier to see the symmetries when you draw the torus in this kind of planar way. So like look at the dual of this. It would look something like this. Okay, yeah, so it's like a bunch of hexagons. And then the symmetries would just be like rotations of this hexagon and translations. Okay, but thank you. So these are complete regular maps, and this is the one I'm interested in, K5 inside of sigma 1. Okay, next, what is this picture? So this, I'll just say it right now. It's the complex plot of the equation y squared equals 4x cubed minus x over 1 plus 2i to the 4th. So I had a lot of trouble organizing this talk, but I decided to present it this way. So there's a lot of things going on, but let's just focus on this. So here, this picture is the complex plot of the polynomial equation y squared equals 4x cubed minus x over 1 plus 2i to the 4th. Okay? So what do I mean by complex plot? So this x and y, they're complex numbers. So, right, so complex numbers, let me make some space. Complex numbers lie on this two-dimensional plane. If you think about it as a real vector space. But whatever, so like complex numbers lie in the complex plane, and I'm plotting the solutions of this polynomial equation. So these are pairs of complex numbers. So if this was C squared is 4-dimensional, right? Because C is 2-dimensional, so C squared is 4-dimensional. So I have pairs of points, x, comma, y, that lie inside a 4-dimensional space. You can also think of it as A plus BI, comma, C plus BI. So there are going to be 4 real numbers, A, B, C, and D. So I'm really plotting 4 tuples in 4-dimensional real space. I'm plotting the solutions to this polynomial equation, right? So this is going to cut out some surface inside of 4-dimensional space. And this is the surface that it cuts out. What I'm plotting here is not, so obviously I can't plot 4 dimensions, right? So what I'm plotting here is the base here is going to be, let me make some space. The way I'm plotting it is I have like the xy plane. This is one copy of C. And then I have the z-axis. This is another copy of C, but it's just the real part. So I have 2 copies of C. I have 1 copy on the floor, and then another copy going vertically. But I'm only plotting the real part of the second coordinate of y. So this is the x coordinate, and this is the y, real part of the y coordinate. So this is how I'm plotting the solutions to a complex polynomial in 3-dimensional real space. I'm forgetting about the 4th coordinate in this picture. So these are the solutions. So this whole surface is cut out by the solutions of this polynomial in C2. And this kind of graph that you see inside here, there's red vertices, blue vertices, white vertices, and these black edges. So the black points are the pre-images of the unit interval 0 to 1 under the rational map. X, y goes to this. So I'm just going to write this down. Don't worry if it doesn't make any sense, but just writing this down. So there's this map so I'm calling this C. C is a set of solutions to this polynomial equation. And then I have a map from C to, C to the complex numbers. And what it's going to do is going to take x, y. So a point on this surface is going to consist of 2 complex numbers, x and y. And it's going to send it to a new complex number that's given by this formula. So it's very complicated, but don't worry about what the formula is. It's just a way, it's just giving me a function on the surface. So 1 plus 2i to the 8x squared times 1 plus 2i to the 5th x squared minus 1 over 1 plus 2i cubed x squared minus 1 to the 4th. So this whole expression doesn't really matter, but what it is just giving me a function on this surface. So I have a surface inside of C4, and it's plotted inside in this weird way. And I have this function that's assigning complex numbers to points on my surface. And what I'm doing here, I'm saying that this embedded graph, all of these black points, they're the pre-image of 0 to 1. So I have, inside of C, I have this unit interval. Right? So remember, C looks like, this is what C looks like. And inside of C, I have this interval, 0 to 1. So I have these points. And these black points that you see plotted on the surface are the points that get sent to this unit interval under the map, this complicated map. So I have this function on a surface that's assigning complex numbers to points on the surface, and the numbers that land inside of this interval, 0 to 1, are the ones that I've colored in black. Does that make sense? No, it doesn't make sense? Okay.
First of all, why is it independent of y?
Why is this function independent of y? Okay, fine. Yeah, so this is just a function that I wrote down.
It's a,
and that's a good question. It's independent of y. Right, so this is a function that it takes in the coordinates x comma y, but it only depends on the x coordinate. So, yeah.
because I don't understand the relation of this function to the 0 to 1.
Oh, yeah. So I'm saying this black graph that you see drawn on the surface, that's the pre-image of 0 to 1. So this is a function on, it's a function on C squared, but also a function on the surface. And the points that
when you enter x from 0 to 1 will be accurate as y.
No. Yeah. So I'm looking at the points, which points x comma y gets sent to some number, I don't know, so let's call this phi of xy. Which numbers get sent to phi of xy, which are inside of the interval 0 to 1. So does that make sense? Okay. And if I plot it, it looks like this, right? So these black vertices are the ones that get sent to the interval 0 to 1. And these blue vertices, they're the ones that get sent to 0. So, okay, so, yeah. Let me write it over here. So blue.
The camera can't see over there.
Oh, okay. So let me.
I mean, I've been doing like a really bad job. Like I've been jerking the camera around sometimes.
Alright, it's fine. Okay, so the blue vertices.
I'm on the way. No.
Get sent to 0. Get sent to 0. And the white vertices get sent to 1. And the red vertices So when I evaluate this function at a red vertex, then it's a pole of the function. It goes to infinity. And when I evaluate this function at a blue vertex, it's 0. And when I evaluate this function at a white vertex, it's 1. Okay, so let's keep going. So let's have a closer look at this picture in MATLAB. So I plotted this picture in MATLAB. So here we go. So yeah, here it is. So on the left-hand side is the plot of the real part, and on the right-hand side is the plot of the imaginary part. So remember, complex functions, you need 4 coordinates to plot them. So the only way I can do it is plotting the real part and the imaginary part separately. Okay. And I can also move this around here. So this thing on the left, this is the surface defined by this polynomial, y squared equals 4x cubed minus x over 1 plus 2i to the 4th. And the points that you see in black are the ones that get sent to the interval 0 to 1 under this complicated map. And yeah. And okay.
And that function, why do you use that function for this?
That's a good question. So I might be able to explain why I get to this function at the end of the talk. But so right now it's just some function, right? But the thing to notice here is that the blue vertices, if I zoom in a little bit, So, okay. Okay, so this is a little bit annoying. So there's this. Okay, but whatever. So just ignore the numbers here. But what you can see is that this blue vertex over here, this is adjacent to every other blue vertex via some edge of the graph. So this blue vertex up here is adjacent to this one over here. So this one up here is adjacent to this one here by this edge. And then by this other edge, it connects down to this point underneath. Right? So over here, there are 2 different blue vertices, and then this one here is connected down to this one like that. And then it's also connected with this edge over here to this blue vertex down here. So there's that edge that connects them together like that. And then there's a 4th blue vertex at infinity that you don't see. But if you walk along this edge up here, you go all the way back up to infinity. So that's the situation with every vertex that you see here. So I understand it's kind of hard to see, but this is actually an embedding of K5 inside of a surface. Now, the genus of the surface is actually also 1, but it's kind of hard to see it. You can sort of see it. Here, you see on the left-hand side, there's this little kind of donut hole in the middle. But the issue is that this surface also goes all the way out to infinity. So you need to add in points at infinity, and then you actually get a torus, right? So, but the cool thing is, like, this is just a polynomial function that I wrote down, and then a polynomial or rational function that I wrote down. And then I did this weird thing. I looked at the preimage of the unit interval, and then that turned out to be a graph inside of the surface, which is just K5 inside of the torus. That's the original graph that I started with, K5 inside of the torus. So let me come back here. So that's, so yeah, so the connection between these 2 pictures is actually the same picture. This is complete graph and 5 vertices inside of a torus, and drawn in this way. Opposite edges are identified, and these points are the 5 different vertices. But here, this is an algebraic description of the same map. It's I have a surface defined by this polynomial, and then I have a rational function defined by this crazy function here. And then the preimage of 0 to 1 are these black edges, and the preimage of 0 is blue vertices, preimage of 1 is white vertices. But just blue vertices matter. They're the vertices that are connected to every other blue vertex by some black edge. And there are 5 of them. So this is an embedding of, it's the same embedding. It's K5 inside of a torus. Okay. Are there any questions?
What
Yeah.
was the other vertices?
Yeah, so
the
the-
white
yeah.
vertices.
The white vertices, you could also draw some white vertices. I need to, let me put it this. So remember, this is, how was it? Looking again. Like this, right? So this is, yeah, so this, let me draw this a little bit. Okay, hopefully that's a good picture. But, so the black vertices are these, or what I had is the blue vertices in the other picture. Or these ones here. And then the white vertices are the midpoints of edges. Okay, it's a little bit harder to draw these. Right, so the white vertices are the midpoints of edges. So there's some midpoints. Yeah, and then the red vertices are the centers of bases.
Oh.
1, 2, 3, 4, 5. So there are 5 red vertices, 5 blue vertices, and 10 black vertices. Oh, or 10 white vertices in this setup. Yeah, those are these images, these points over here. So these, there are 5 red vertices, 1, 2, 3, 4, 5. So in this picture, there's 1, 2, 3, 4, and then these 4 vertices are identified with each other. Yes?
So these surfaces are like going to infinity?
Yes.
Or they're going back and connected to the
Yes, yes.
Which
So really, I should be viewing these surfaces inside of complex space. I should view them in projective, in 2-dimensional projective space, and this adds in points at infinity. So then the surface also has points at infinity, and it actually, instead of looking like this weird double-sheeted thing, it actually looks like a torus. But it's kind of to actually see why this polynomial equation, this is called an elliptic curve. To see why this elliptic curve is just a torus.
so it's actually closed surface.
Yes. If you add in the points at infinity.
How many points at infinity? Is there only one?
Yes, there's only one point at infinity. On this one, there's only one point at infinity. It's the point infinity, infinity. Yeah. So this is really just going to the affine picture here without points at infinity. It just looks like a torus minus a single point. But it's a little bit hard to see with it going off to infinity and it being like this double sheeted cover. But okay, so that's that's that. And we can also write down coordinates of the graph. So I just wrote this down to the explicit. So these are the zeros. These are the pre-images of, so these are the x-coordinates of the zeros. Okay, it's not really that important. I won't go through this. But the point is that they're the same picture. So this is a purely topological description of K5 sitting inside the torus. And this is an algebraic geometric description. So algebraic geometry is about studying polynomials and the solution sets of polynomial equations in several variables, maybe. So this is a polynomial in 2 variables, and it has complex coefficients. And this is an example of what's called a variety. So it's a solution set of a polynomial equation. So all this terminology doesn't really matter, so it's just math lingo, but yeah, this is an example of what. So this is an object in algebraic geometry. This is an object in topology, and actually there's a lot of different areas of math that's converging in this 2 same picture kind of thing. So to explain why, there's a lot of topics that I have to cover. So the first is topological graph theory. Let me actually draw a picture of all of these topics. Let me state them out loud first. So topological graph theory, Riemann surfaces, algebraic geometry, complex analysis, Galois theory, number theory. So obviously I'm not going to be able to say all of this stuff, and this is an undergraduate talk, so it's probably not best to just unload all of this onto you right now. And there's only like...
That clock doesn't work.
9 minutes left. What time is it now?
9 minutes left.
9 minutes left. Okay.
You got this.
Woo! All right. So, yeah, I really don't have the time to explain all of it. And so I'm just going to maybe draw a picture of all of the topics involved here. And maybe this is interesting to you to see how interconnected math is. So here we go. I'm going to draw a picture of, so this is just some diagram that kind of helps me situate myself in all of these topics. So over here, I'm going to have topological graph theory. So topological graph theory is, I had a slide on it a little bit way before. Did I? Yeah, here. So I just sent tons. Topological graph theory studies embeddings of graphs and surfaces. That's kind of like half of what the talk was about today. These embeddings of graphs and surfaces, or maps, as I call them. This is in the realm of topological graph theory. So not only are you studying graphs, but also you're putting graphs inside of surfaces and studying those objects, the maps. So that's topological graph theory. What else do we have? So this is connected to Riemann surfaces. So I have one more slide here on Riemann surfaces. So what are Riemann surfaces? They're one-dimensional complex manifolds. So what that means is just, it's a surface, but locally there's also the structure, this complex structure to it. So for example, the Riemann sphere, so this is just a complex plane with a point at infinity. So you have 0, 1, I, and -1 here. So this is just the regular complex plane. But I add in a point at infinity, and I get a sphere. So the point is, like, if I go in any direction in the plane, I'm going to end up at the point at infinity if I go infinitely far. So that's this Riemann sphere. And the Riemann sphere has genus 0, and it's a surface. The point is, Riemann surfaces are surfaces, they're topological surfaces, but they also have complex structure. So locally, you can put complex coordinates in any small neighborhood over here. So a surface is something that looks locally like a part of the real plane, but a Riemann surface is something that looks locally like a part of the complex plane. And these charts have to behave nicely together. They have to be holomorphic transition maps. But the point is, there's it's surfaces with extra structure. There's a complex structure to it. And so this is genus 0 Riemann surface, a sphere. This is genus 1 Riemann surface. And another name for this, so this is a torus with a complex structure. And another name for the torus, or Riemann sphere, a Riemann surface of genus 1 is an elliptic curve. So the example that I had over here, this is an example of a Riemann surface of genus 1. So somehow this polynomial, this y squared equals 4x cubed minus x over something, this, when you add in the point in infinity, has to look like a torus. And this picture over here is kind of suggestive because the usual picture of an elliptic curve, the real points of the elliptic curve at least, you might have seen it. It looks something like this, right? But those are just the real points of the elliptic curve. You also plot the complex points. It looks like a torus. So this point goes out to infinity, so this is like the real points are just like a cross section of this torus. Okay. Anyway, so yeah, that's it. And yeah. So that's the complex Riemann surface. And the connection between Riemann surfaces and topological graph theory that I use are desins. But yeah, there's also connections to all of these other topics, is algebraic geometry. So I really don't have enough time to say anything about this, but hopefully this will just interest you, and maybe you would want to study this in the future. So I'm just, right now I'm writing down a bunch of words, but the point is, don't worry, if none of this makes sense. These are just, okay, my handwriting is pretty bad, but like, the point is, so there's Riemann surfaces, and they're connected to topological graph theory using this notion of dessin, which I actually didn't explain at all. But, right, and then Riemann surfaces are also connected to algebraic geometry, complex analysis, Galois theory, and number theory. Okay, I don't think I should go on anymore. So let's end here. And if people want to talk with me about this stuff in more detail, I'm willing to stick around and answer some questions. All right, thank you. Okay. Yeah.